Hi all.
Hey.
Okay, can you guys hear me clearly?
Yes.
Loud
Yes.
and clear.
Okay. I just like to share my slides quickly to see that that's working. Host disable participant screen sharing.
I'll
Sorry, do you want to try it again?
Okay, I'm trying. Okay, is it that? Can you guys see that?
Looks good.
Yep.
Okay. Cool. Okay. Thanks, guys.
Hi, this is Kaushal. Can I check my slides?
Yes, go ahead.
Is it visible?
Do you want to put it into presenter mode just to make sure?
Yeah, somehow I'm not able to do that. Just a minute.
There you go. F5 usually, but from
Yeah, somehow.
And
Does it work
yeah.
fine?
Mm-hmm.
Okay, thanks.
Awesome.
So I'll stop sharing. Thank you.
Hi, Chris. Did you want to do any testing?
Yeah, that would be good. How's that? Do you see the right screen?
Yes, looks good.
Great.
Chris, do you want to start sharing your slides, and I'll give people another minute before I introduce you?
Sure.
Okay, let's get started. I'd like to introduce Chris Bochenek, who is a graduate student at Caltech, and he defended his PhD on Tuesday, and he's still willing to talk to us early in the morning about the instrument that he built that detected the first observed galactic fast radio burst. So, thank you, Chris, and take it away.
Yeah, thanks a lot for inviting me. So today I'm going to talk to you about my thesis work, which largely involves this instrument known as STARE-2, or the Survey for Transient Astronomical Radio Emission 2. And it's kind of a wild idea of trying to find the whole idea behind the instrument is to take a risk and try and find an extremely rare phenomenon, which would be a fast radio burst in the Milky Way. And we were fortunate enough that that's exactly what we did. So a good place to start would probably be, what is a fast radio burst? Fast radio burst is mainly an observational classification. What they are is millisecond duration radio bursts that come from extragalactic distances. And because they come from so far away, that must also mean they're extremely powerful. And they were first discovered when Duncan Lorimer was searching through archival pulsar data, looking toward this small Magellanic Cloud. And instead of finding pulsars, he found something more interesting, which was this radio burst on the right here. And the thing that about this radio burst that tells us that it's astrophysical is that you can see that the emission is more and more delayed as you go to lower and lower frequency, which is characteristic of radio waves traveling through the interstellar medium. And the amount of delay that's between the high frequency and the low frequency, the length of that delay is determined by the number of electrons between us and the source of that radio burst. If you count up all the electrons needed to explain this dispersion sweep or delay between the high and low frequencies, then you need way more electrons between us and the source of this radio burst than exist between us and the small Magellanic Cloud, implying that it came from a great distance. And because it came from a great distance, in order for us to see it, it must also be intrinsically very bright. I'm sorry, could you please mute? Yeah, the whole question is, what could be so powerful as to produce a radio burst that we've never been able to see before, that's coming from such a distant place? So that's like kind of the characteristic of these fast radio bursts, is that they have extragalactic dispersion measures, meaning you need a lot more electrons to explain their dispersion sweeps than exist in the Milky Way. They're about 1 millisecond in duration and have been observed between 100 megahertz and 8 gigahertz. However, they've been primarily studied at 1.4 gigahertz, and the detections elsewhere, except for the 400 to 800 megahertz band, are kind of sparse. So I don't think the frequencies of FRBs have been particularly well explored. And there's about one detectable FRB on the sky any minute. You just have to be looking at the right place. And I define detectable to mean a fluence of greater than 2 Jansky milliseconds. Some fast radio bursts repeat, and sometimes you can stare at a fast radio burst source and pick up 10 different radio bursts in one observation. And sometimes you can stare at a fast radio burst source for months and you'll see nothing. So not all fast, in fact, most of the fast radio burst sources we know have not yet repeated. And here you can see a collection of bursts from a well-known the first known repeating FRB 121102. And you can see that there's a lot of different burst morphologies from these repeat bursts. Some of them, like this one, appear quite band limited, whereas others are seen over a wider bandwidth. There's all sorts of interesting spectral structure and subbursts, and this one appears to be drifting a little bit. So I wouldn't say there's any such thing as like a typical fast radio burst morphology. Recently, we've started detecting fast radio bursts with interferometers instead of single dishes, which means that we have the ability to pinpoint them to a particular galaxy, and they've been seen from a wide variety of different host galaxies. This fast radio burst up here appears to be in a star-forming region in a spiral galaxy, whereas this FRB appears in the halo of its potential host galaxy. And this is the host galaxy of that repeating FRB 121102, which is in a metal-poor dwarf galaxy. And then another fast radio burst was found kind of near the half-light radius of a massive galaxy without a huge amount of star formation. So there's all sorts of different places that fast radio bursts can come from. So the central question of my thesis is, what are the actual objects that are making these fast radio bursts? And it's particularly difficult to study. It's particularly difficult to study phenomena that are extragalactic in nature because you can't really like zoom in and see exactly what's going on. And say this object produced this fast radio burst. But the idea behind our experiment is that if you could find a fast radio burst in the Milky Way, then you could go and point every telescope in the world at it and figure out exactly what it was. So this is our instrument, the Survey for Transient Astronomical Radio Emission 2, or STARE-2. It consists of 3 antennas made out of a 6-inch metal pipe and 2 cake pans, located one at the Owens Valley Radio Observatory, another at the Goldstone Deep Space Communications Complex, and a third near a town called Delta in Utah. The whole idea behind the experiment is to trade the sensitivity you get when you observe with a dish for the field of view of a dipole antenna in order to catch extremely bright and extremely rare fast radio transients, such as a fast radio burst in the Milky Way. And to that end, we can see about a quarter of the sky at any given time, and we're sensitive to radio bursts above 150 kilojansky milliseconds in fluence, which compared to I defined a detectable fast radio burst earlier as 2 Jansky milliseconds. So this is quite a few orders of magnitude above. We're only sensitive to radio bursts quite a few orders of magnitude above what the flux levels that most fast radio bursts are detected at. So our stations are spread out across a wide area in the United States, and you can see the light travel time between each station here. And the primary reason to do this is to filter out radio frequency interference, as if you have a car start at the Owens Valley, that you're not going to see that in Delta, but a galactic fast radio burst should be visible from this entire area. And we observe between 1280 megahertz and 1468 megahertz, which is a popular band for FRB searches. The receiver actually goes up to 1530 megahertz, so that's 250 megahertz of bandwidth, but that entire top part of the band is just polluted by RFI that we just block it out. The time and frequency resolution of STAIR2 is among the best compared to other fast radio burst experiments, which means we're particularly sensitive to shorter duration events that other surveys might not be. And we search out to a dispersion measure of 3,000 parsecs per centimeter cubed, which should be sufficient for detecting things in the Milky Way and possibly beyond. And we're sensitive to transients on the timescale from 65 microseconds to 34 milliseconds. Once you go beyond 34 milliseconds, then the rate of radio frequency interference just ticks up and it's unmanageable. We run an independent search at each station, and we also have so much data going through our system that we can't store it and save it for reanalysis. So we're trapped into, if something was going to happen, we would have to notice it and save it to disk within 13 seconds. Otherwise, we'd just build up too much data. So after each station runs its pipeline, and then we can compare the candidates that each station detects. And if there's a coincidence between more than one station, then we take a note of that. And once a day, all of these coincidence events that happen at more than one station are compiled into a daily report that happens at 5:30 a.m. Pacific time. And we're only saving the 65 microsecond total intensity data, so we're not doing polarimetry or interferometry. So this is the block diagram of our system. We have the signal goes into the feed, which is amplified by a low noise amplifier, which then goes to another box of electronics, which does some more, it has a filter that cuts out of band RFI and further amplifies it, and then it's sent by, and then that further amplified signal is sent over fiber to a server room where we have another box of electronics that has our down converter that we down convert to 250 to 500 megahertz in this backend box, and then have a sharp filter to really define our band. And that gets sent to a snapboard to be digitized, Fourier transformed, and channelized, and integrated into our 65 microsecond total intensity data product, which we then send over to a server. So that should have kind of been the end of the story. Maybe we'll detect, like, the probable outcome of this experiment was we probably won't find anything. We'll be able to say something useful about the luminosity function of radio bursts and how often they happen in particular galaxies. But nature surprised us. It was a pleasant surprise. And on April 28th, we actually did make a detection of a galactic fast radio burst. The burst happened at 7:34 a.m. Los Angeles time on April 28th. And within 13 seconds, as our system was designed, the burst was found by each of our 3 stations independently and saved to disk. And this burst was tremendously bright. It's not every day you get to use the units of megajansky to describe something other than the sun, but this burst had a fluence of 1.5 megajansky milliseconds and had a dispersion measure that was consistent with originating within our galaxy. So I think this figure sets the scene for this burst. On the right here, we have the sky in altitude and azimuth at Owens Valley, and these 3 arcs correspond to a single baseline's localization region. And this burst is known to be associated with the galactic magnetar SGR J1935 plus 2154. And you can see the location of that magnetar here. And it is consistent with our localization region. And furthermore, it happened inside of our 3 dB beam width. And we're not the only experiment to detect this radio burst, which is kind of how we know it's associated with SGR 1935 plus 2154. The CHIME collaboration detected this FRB as well, but it happened far outside of their field of view, which you can see here. And crucially, the sun, which is a frequent source of stair-2 triggers, was outside of our field of view at the time, and is highly inconsistent with our localization arcs. And if we move over to the left, you can see stair-2's 95% localization region, which, though crude, is consistent with the known position of the magnetar SGR 1935 plus 2154. And you can see CHIME's localization is a bit better, and coming from the magnetar. However, I think the best association between this FRB and this magnetar comes from the FAST telescope, which a few days later, after the FRB, detected another burst that was 7 orders of magnitude weaker, but it had the same dispersion measure as the FRB. And because FAST is such a large telescope, its beam size is 3 arc minutes. So we know that radio bursts with this dispersion measure are coming from within 3 arc minutes of the known position of this magnetar, which is, I think, why we're comfortable saying that this burst came from this magnetar. So another peculiar thing about this fast radio burst was that it's the first fast radio burst to have a counterpart at other wavelengths. So not only was there, at the same time as the radio burst, there was an X-ray burst as well. And this X-ray burst was a bit strange. It had a bit harder spectrum. It had a much harder spectrum than a typical X-ray flare from this magnetar. And one particularly interesting thing about this radio burst is that it has this substructure here with 2 peaks that seem to align kind of well with the time of arrivals of the radio bursts that were seen. So CHIME saw 2 bursts separated by 30 milliseconds, and stair-2 only saw 1, which you can see here. And the time of the radio burst seems to line up pretty well with the peak of this X-ray emission. However, the radio emission does happen about 7 milliseconds before this X-ray peak, which may mean something, it may not, but I'm sure theorists will have fun with it either way. So now I want to switch gears and convince you that this is a fast radio burst. And the first question you might ask is, could it have been seen from extragalactic distances? And the answer is yes, it could have been seen by the FAST telescope out to about 70 megaparsecs, so we can check that box. So here we have the radio transient phase space. So on the y-axis here, we have the luminosity of a radio transient, and on the x-axis, we have its duration. And you can see that our event shown here is most similar to the fast radio bursts, although it is weaker than a typical fast radio burst. However, the reason there's a cutoff here in the FRB distribution is not because lower luminosity FRBs don't exist, but because our telescopes are not sensitive enough to find them. And we do actually expect a galactic survey like STARE-2 to be sensitive to this low luminosity population. Because if you took the rate of extragalactic FRBs and asked the question, how long do I have to wait to see an FRB in a particular galaxy? The answer is much longer than a PhD. However, if low luminosity FRBs are more common than high luminosity FRBs, then there is hope that you would detect an FRB in a particular galaxy on a PhD timescale. So basically, we could be only seeing the tip of the FRB iceberg in our extragalactic surveys, and our galactic surveys are uniquely sensitive to this low luminosity population. And based on this assumption, we made a prediction in our instrument paper that galactic fast radio burst would probably have an energy of about 10 to the 26 ergs per hertz, and this radio burst did have an energy of about 10 to the 26 ergs per hertz. And this can also be kind of seen in this figure, which shows the luminosity function of fast radio bursts. So based off of only based off of our detection and the known properties of STAIR2 search, we can say that we started observing in January 2019 and had to wait until April to see a burst, which can get us an all-sky rate of these radio bursts. And then if we assume that fast radio bursts track star formation, which is pretty likely scenario for a magnetar that has a known supernova remnant, we can turn that all-sky rate into a volumetric rate of about 10 to the 8 of these SGR 1935-like events per cubic gigaparsec per year. These black points here are derived from a sample of ASCAP extragalactic fast radio bursts, and this luminosity function is fit only to these black points. And you can see that our event is consistent with these constraints, which I think means that if you accept that fast radio bursts come from magnetars, if you accept that this event is related to extragalactic fast radio bursts, you kind of have to accept that this is the dominant mechanism, because there are just too many of these types of bursts that there's not really room for another dominant channel. And another way we can, so with all that said, I think we're starting to paint a picture that magnetars are probably responsible for most fast radio bursts. So then you can go and ask the question, are the host galaxies of extragalactic FRBs consistent with a magnetar hypothesis? And we know magnetars are young objects, so they should be associated with star formation. So we're then asking the question, are extragalactic FRBs consistent with the star formation in the universe? So this is a plot showing the host galaxies of fast radio bursts in terms of their star formation rate and stellar mass, compared to other types of transients, in particular core collapse supernova, which is where we think magnetars are born. And we want to compare the hosts of these fast radio bursts to the hosts of these different types of transients. However, you can't directly compare galaxy samples at different redshifts because the population of galaxies evolves with cosmic time. So we developed a technique in order to correct for this. And in the background of this plot, you can see our distribution of core collapse supernova and the raw measurements of the host galaxies of fast radio bursts, which then go through our procedure and get transformed into these triangles, which should be comparable to the distribution of core collapse supernova. And then you can run a bunch of statistical tests and say that the probability that the triangles are drawn from the blue distribution is greater than 20%. So that's, I think, enough to answer the question, at least for now, are extragalactic FRBs consistent with star formation? Yes, because they're consistent with host galaxies of core collapse supernova, which track star formation. So with all this, I think we can conclude that most FRBs probably come from magnetars, as they could be seen from extragalactic distances. This FRB was less energetic than other FRBs, but we kind of expected this based off of both the properties of extragalactic FRB surveys and galactic FRB surveys. The volumetric rate of these SGR 1935-like events agrees with the volumetric rate of extragalactic fast radio bursts. And the host galaxies of fast radio bursts appear to be consistent with tracking star formation, which is what you would expect for a magnetar origin. So with all that said, I just wanted to take a moment to say thank you to everyone who helped out with the STAIR2 project, as even a small student-led project takes a village to execute, and this wouldn't have been possible without everybody's contributions. So I'll stop there and take questions.
Thank you, Chris. That was a really great talk. I'm going to read some questions from the chat. The first one is, do you dump voltage data for detected bursts?
No, we only have the integrated total power burst, which is kind of why our localization is as crude as it is, because we're basically just measuring the time of arrival with that chunky data and matching those times of arrival at different stations to a place on the sky, which is pretty crude.
And the next question is, when you say an association with core collapse supernova, are you inherently associating with superluminous supernova?
No, superluminous supernova are kind of their own beast, and another interesting hypothesis that we tested out. So type 1 superluminous supernova, which is hydrogen poor superluminous supernova, happen in kind of special galaxies. There are these yellow points over here. They tend to happen in highly star-forming metal poor dwarf galaxies, which does not simply just track the star formation in the universe, implying there's something a bit special about their progenitors. But the like run-of-the-mill core collapse supernovae are known to just track the star formation in the universe. They're just a counter of massive stars, essentially. And one of the hypotheses behind why hydrogen poor superluminous supernova might be so special is because they're engine driven. And one of the popular ideas for what that central engine driving the energy, why they're so superluminous, is a millisecond magnetar, which could potentially be related to fast radio bursts. Like if we think magnetars come from, if we think it's possible that magnetars are related to superluminous supernova, then it's possible you would eventually see a fast radio burst from a superluminous supernova source some decades later. And this gets into like a superluminous supernova powered by a millisecond magnetar is a bit different from the types of magnetars that we know in the Milky Way, which we think the magnetars in the Milky Way get their magnetic fields from just inherently from their progenitor massive star, which might have particularly strong magnetic fields, but a millisecond magnetar in a superluminous supernova would probably get its magnetic field from a dynamo instead of directly from its star. So I think that by studying if we keep studying fast radio bursts and their host galaxies, it's possible that eventually we'll find a connection to type 1 superluminous supernova, which would be kind of evidence of a new magnetar formation mechanism.
Thank you. Are there any other questions? Well, I can ask a question. I didn't quite understand the adjustment for redshift that you had to make for the host galaxies.
Yeah, I kind of glossed over that. So essentially, if we're comparing a complete sample of fast radio burst host galaxy to a complete sample of core collapse supernova host galaxies, but the complete samples of core collapse supernova are very much in the local universe, while the sample of fast radio burst host galaxies goes out to redshift like 0.66. Mm-hmm. And you can see the star forming main sequence from z = 0 is very different from the star forming main sequence at redshift 0.66. So you would expect on average if FRBs track star formation and core collapse supernova track star formation, the galaxies that produce fast radio bursts at higher redshift would probably be more massive and more star forming on average than a type of transient that tracks star formation at redshift 0. So there's a systematic bias in how you're selecting their host galaxies.
I see. So you would assume a lot more core collapse supernova at higher redshift, but those aren't the galaxies that you can compare to.
Yeah, so essentially what we do is just place the fast radio burst host galaxy in the distribution of where star formation happens at that redshift, and then transform it into the distribution of where star formation happens in the local universe, which is why everything in this plot is kind of moving down and to the left, since star formation in the local universe tends to happen in lower mass galaxies and is not as intense.
Mhm. Thank you. This was a really great talk. And unless there are any last questions, we can move on to the next speaker.
Thank you very much.
Our next speaker is James Smith from the South African Radio Astronomy Observatory.
Can everyone see and hear me?
Yes.
Okay, great. Good day. My name is James Smith, and I'm going to talk about containers. I envisioned this not quite as a tutorial, but something of an introduction to why containers might be interesting for us, because it's a concept that our team at Soreo has started using rather recently. The colleagues of ours in other departments have enjoyed it for quite some time now. I don't like agenda slides, so let's dive right in. Before we get to the idea of containers, though, I want to talk about how software actually runs on a computer. This is quite a vast topic, so I am of necessity oversimplifying, but it helps to think of it in layers. Hardware is at the bottom. This is the silicon and metal that's actually conducting electrons from place to place. The kernel is the very lowest layer, which provides an interface to the hardware needed by higher level software. Above that, you get libraries like glibc, which talk to the kernel to get stuff done. They provide functions to applications such as open, malloc, socket, that sort of thing. The applications don't even really need to know what hardware is underneath them in most cases, not even which kernel. The libraries provide fairly standardized interfaces for applications to use. They ask for some memory, and they get it. They ask for a socket file descriptor, they get it. Similar with opening a file, whatever. Libraries can also come in several layers. glibc is a very low-level one. You get higher-level ones like X, which provides a platform for graphical applications to ask for windows and buttons, etc. On the highest level, the application is the software which makes a computer actually useful to us. That is, it takes some inputs and produces some outputs which are useful in the wider world outside the computer. Applications programmers don't typically need to worry too much about Maxwell's equations to move the electrons around when they write their software. We can start from much higher levels of abstraction relevant to the useful task at hand that we are trying to accomplish. The problem with this is that usually one application by itself doesn't keep a computer as busy as it could possibly be. Even if the software is free, and we like free software around here, we did spend money on the hardware, so we should get all the value that we can from it. We could simply run multiple applications. This is perfectly valid. Computers do this all the time. This increases utilization or the value that you get from the hardware. The same box that you spent your money on is now doing more work. Now, this works very well if all the applications you need run in the same environment and don't tread on each other's toes. But what happens if you have applications which need different versions of the same libraries, or if the libraries can't coexist? So I'm going to illustrate the point with an extremely contrived example. Imagine that your e-commerce website has two PHP apps that need to be run, one for giving a front end to customers and the other one for doing management of stock, which is used by staff. Business is booming and you'd like to expand your business to other countries, but our apps are written in PHP 5, which doesn't support Unicode, which is necessary in languages other than English. That's fine. We can update our PHP to version 6 while we rewrite our front-end app to support foreigners' funny names. We were going to do that anyway. And the stock management app should be fine to run with newer PHP, right? Probably not. Now we have some kind of conflict which prevents our two apps from coexisting peacefully on the same computer. We could try to port both apps to the new PHP, but that costs time and money, which we could probably do better things with. Or possibly app number 2 is a proprietary one and the vendor isn't planning to release a new version for the next 12 months, which is far too long for us to wait to expand into new markets. It will give our competitors a ridiculous head start. Our hands are tied. What are we going to do? Well, we could separate our applications so that they each run on their own computer, with each one having the exact dependencies that it needs, no more, no less. The two applications can talk to the database via the network. This will work, but now we're back to where we started. We've spent money on far more computing power than we actually needed. It's also a hassle to maintain more servers. We have more chances of failures happening, which might interrupt our business. We can plan for this by having some redundancy or failover mechanism, but it just compounds the underutilization problem because we've now bought more computers than what we really need. So along came virtualization with a few more layers. On top of your operating system, which is often quite minimal in setups like this, you have a hypervisor application, which emulates virtual hardware. On top of this virtual hardware, you can install a normal operating system, libraries, applications. Usually the hypervisor makes provision for networking the virtual machines or VMs with each other and with the outside world. So now what you have is multiple virtual computers, each with their application running in an isolated environment for the price of a single server. So you get all the benefits of running multiple computers with none of the cost penalties. You do pay for it, however, somewhat with performance. Applications running in a VM will not be as fast as those running bare metal. The other consideration is that VMs are heavy and expensive to get going. They take a while to boot up and shut down. Setup can be automated to an extent, but creating a new VM does take time. The next step along the evolutionary chain from virtualization is containerization, and now I finally get to the meat and potatoes of my talk. Looking at things one way, containers are like light VMs. Looking at it from another perspective, containers are an evolution of the Unix chroot concept. For the sake of time, I won't go too deeply into that now, but the important idea here is that containers share the host OS's kernel. They provide their own libraries and applications though. So instead of virtualizing hardware for a guest operating system to run on, you only need a fairly thin container runtime to give you, for most practical purposes, the same isolation functionality. And all else being equal compared with virtualization, a containerized application will realize performance which is so close to bare metal as to be basically the same. Additionally, containers can be created and destroyed in seconds as opposed to the minutes which are typical for a well-automated VM instantiation. It's much easier to stop and start them than applications contained in VMs. Containers aren't without their limitations, but they're mostly easy to overcome if you approach this logically. So up to now, I've looked at containerization as a way to solve a problem of underutilization of hardware and isolation of environments of applications because it originally came about in response to these challenges. This might not necessarily hold much interest in the Casper community, which tends to be largely focused on radio astronomy, with a few welcome interlopers from other fields where scientific computing is important, of course. This kind of application can usually keep your computer fully busy quite easily. Many computers even, we usually prefer to buy more computers, not fewer. Furthermore, since we take great pains to write our software from scratch each time, we don't usually run into issues with one package having conflicting requirements from another one. And we don't like doing updates either. So once it works, it's deployed for decades at a time. I say this with slight tongue in cheek because Casper generally isn't quite like this. But during my time in radio astronomy, I found myself looking at Fortran code from the 70s more often than I'd like. So I have to admit that the tendency does exist in the scientific community in general. So what attraction could containerization hold for us? To answer that question, I'll refer for the first time now to the company and product known as Docker. Docker isn't synonymous with containers. They didn't invent the concept, but Docker has done a lot to make containers generally more awesome, to the extent that it has become more or less the de facto standard. Docker defines the way that most container images are built using layers. For example, you start with an Ubuntu image, add Python packages, add CUDA, add your specific application from GitHub, build the image, and then you have the ability to deploy your application with a single command. Git-like versioning of Docker images makes reproducibility quite easy, along with updates and rollbacks if needed. Distribution of images and the software contained therein is facilitated through Docker Hub or your own repository if you like. This works both ways. We can easily borrow the best open source software out there, and we can easily share the software we develop with collaborators or anyone interested. Portability is enhanced. In general, it doesn't matter whether I'm running Fedora, Ubuntu, SUSE, or whatever. This, to an extent, applies even if I'm on a different CPU architecture, such as ARM or x86, although there are some limits to this. It's not universal. Docker has also made container networking quite easy, as well as the monitoring and logging of output from the applications running in those containers. Here's a screenshot of an example Docker command to fire up our prototype GPU X engine that Amish talked about the other day on one of our dev servers. I show this to give you an example of how easy it is to start up a container and get something useful done, but also to illustrate that there are some caveats. In our case, we need low-level access to the networking hardware. We make fairly extensive use of IB verbs, so Docker's abstracted networking implementation won't quite cut it. Fortunately, passing individual hardware devices to the container is quite straightforward. The same is true of GPU hardware. Hit enter and the X engine can get busy doing its work. So what's the point of all this really? Firstly, containers present an opportunity for us to borrow practices from the software development industry, which can help us get our DSP pipelines up and running more quickly and more able to respond to changing requirements in an agile way, to borrow another software development term. It also makes it easy to integrate your software into, for example, a CI/CD pipeline such as Jenkins, which Ishmael will be talking about slightly later today. This allows us to test the software to death without testing ourselves to death. This can enhance the confidence we have in the quality of our DSP pipelines. Every time we make a change, we can be confident that we haven't broken anything because the report we get every morning from last night's automated tests confirms that the DSP pipeline still works. Reproducibility is enhanced. When you're performing experiments, you know exactly what version of the software is running. The way the Docker containers work makes it difficult to monkey patch things or run dirty versions of software. Not impossible if you're determined, but that sort of behavior is strongly discouraged. So the environment is therefore set up so that you can reproduce it very easily. If you notice something funny in your data, you can come back and investigate if there was something wrong with your software, fix it, test it, and deploy your fixed version. Maintenance is also easier. Updates can be done fairly trivially, as well as rollbacks in case the software doesn't work. This doesn't just apply to our DSP pipelines, but can also apply to our development tools, as well as the availability of tons of cool off-the-shelf containerized stuff, which can help with a lot of things. For example, network monitoring, disk-based reporting, event logging, alert triggering. It's all there on Docker Hub. It makes our lives much simpler, no need to reinvent the wheel.
1 minute.
Well, thanks, Catherine. Once you've drunk the Docker Kool-Aid, the next step along the path to enlightenment is container orchestration, and Kubernetes is the flavor of the day in that regard. John mentioned it quite extensively recently. This is an avenue that at Sereo we haven't yet fully explored. It's a tool embraced by many industries, from data science to IT admin. And in a cloud setting, it has many cool features, but we are not building a cloud, we're just staring at them. Some of the features are attractive. For example, if a failure of a container is detected, it can be restarted, even on another computer if necessary in the event of hardware failure. This can save valuable observing time from being lost. There are some downsides though. Kubernetes is an incredibly complex piece of software, so it's a steep learning curve, and it doesn't give easy access to the low-level networking, as I showed in a couple of slides ago. So from a Sereo perspective, we're not completely sold on this yet, but who knows? We watch this space. Maybe next year I'll be telling you how we run MeerKAT extension correlator with Kubernetes, but also maybe not. To finish off, if I can summarize what I hope you'll take away, is that our experience at Sereo using containers is that it's making our lives easier, helping us to deliver better software pipelines with fewer issues than we have experienced previously. And we recommend that you give the technology a try if you haven't already. Thank you.
Thank you. We have a couple of questions in the chat. The first one that I see is wondering if you or others in this community have considered reproducibility and isolating versions of software stack with Nix package manager as well.
That's a fairly complex question, and I'm going to stop sharing so that I can look at the chat.
And Christopher League, if you want to unmute and just maybe easier if you just ask this question yourself.
Nix package. I can't say that I've ever heard of the Nix package manager. There are other ones. I mean, Podman is a competitor, and Containerd and a bunch of other things. They're all largely interchangeable, and the general principles apply to many. The reason we like Docker is it's just sort of the de facto standard. It's so well supported by everyone and everything. So Lincoln, performance degradation when using containers Docker for some particular applications, e.g. network streaming. We can't see any, Lincoln. They seem to be pretty much, like I said, very, very close to bare metal. In fact, we haven't really been able to notice a difference between running our F engines and X engines, in fact, straight on bare metal versus running them in a container. Yeah.
I had a question. I've seen things called Linux containers, and I just wondered how that differs from the type of container that you were talking about.
That is exactly the kind of container that I'm talking about. LXC is, in fact, Docker started off being based on LXC, and it's a different way to implement the same sort of general concept. The use case for LXC containers is generally slightly different. So you use them more like you would a virtual machine, if you will. So for something that's long running, or if you want to run a virtual desktop on a server somewhere, LXC containers are generally good for that, whereas Dockers are sort of designed to be spun up when you need them and destroyed when you're done. But at the base, they're doing fundamentally the same thing. They've got their own kind of libraries and applications, and they're just sharing the host kernel to give you a bit of an isolated environment.
Okay, thanks. Are there any last questions? So our next speaker is Dan Werthimer, who is the Astronomy Department and Space Sciences Lab Chair at the University of California, Berkeley. And also a few weeks ago, he received the Frank Drake Award for his SETI research, and I believe he is the founder of Casper. So let's welcome Dan to talk about PANOSETI.
Thanks a lot, Catherine. I'm actually co-founder. There are a lot of people involved, but I'll take the credit. And thank you, Catherine, for organizing this meeting and bringing us all together, at least virtually. I want to talk to you about this question: are we alone? Is anybody out there? And specifically, I want to talk to you about a new experiment we're developing now called PANOSETI, and it's a all sky all the time, very wide field of view, searching for optical transients with nanosecond to microsecond, millisecond timescales, with a lot of FPGAs and GPUs and switches, kind of a Casper looking thing. It's a joint project of Harvard and Berkeley and Caltech and UC San Diego. It's headquartered at UC San Diego. Shelley Wright is our PI. Ryan Lee, who's highlighted there in the list, is one of the guys behind PANOSETI, but he's also one of the guys behind this conference, working behind the scenes to get all the technical stuff and organize this meeting. There are a couple of different windows where you can do SETI. Most of you know a lot about the radio window that gets through the atmosphere and the ionosphere, but there's also obviously an optical window that gets through the atmosphere at visible wavelengths, and also at near infrared wavelengths are good places to do SETI. And I'm not the first guy to realize that. In 1959, Cocconi and Morrison came out with a paper saying we should look at radio waves, in particular at 1420 megahertz. That's the paper on the left. But just 2 years later, in 1961, Schwartz and Towns suggested that you could use masers, which were at the time before the word laser, but it was the same thing. Charlie Towns was the co-inventor of the laser, got a Nobel Prize for that, and suggesting that lasers would be a good way to communicate between the stars. And Charlie Towns's office was right next to mine. And for years he said, Dan, you ought to work on this optical SETI experiments. And I didn't pay much attention because lasers at the time were little dinky things like laser pointers, and I didn't really see how they could communicate between the stars. But Charlie was right. Now we have petawatt lasers. And so about 20 years ago, we started doing these optical SETI experiments, thanks to Charlie's prodding. Infrared is particularly good, a little bit, perhaps better than visible if you want to go through the dust in the galaxies. This is a plot of the transmission in the interstellar medium. Anyway, near infrared is very good. It goes right through everything, much like radio. So a lot of pros and cons of optical communication between the stars versus radio. Optical is really good for directed communication. Like Arecibo here has a gain of 70 dB. The Keck 10-meter telescope has a gain of 150 dB. Obviously it's the wavelength is much shorter. It's a smaller dish, but the wavelength is small. Also, there's very little dispersion at optical and infrared wavelengths. If you send a nanosecond pulse at a visible wavelength, across the galaxy, it'll still be a nanosecond. That's very different in the radio. If you're an FRB and you send a millisecond pulse, it gets stretched out over minutes or even hours, depending on the frequency, because of the dispersion. There's incredibly powerful lasers. These petawatt lasers could communicate across the galaxy, very good for high bandwidth communication and easy to detect. If you're looking for a pulsed laser, you just look for a flash that's maybe 10 photons hitting your telescope in a nanosecond. That's pretty easy to detect with a simple detector. And there's no natural background. There's no star or anything we know about that sends you 10 photons all in a nanosecond. This is a plot of lasers growing exponentially over time. We've been doing this for a while at visible and near infrared, but these experiments mostly at Lick Observatory, Harvard's got one. But the problem with these experiments is they look at one place at a time. We've looked at 1,000 stars. And if you're looking for something rare, maybe a pulse that goes off once a day or once a week or once a month or once a year, probably the telescope is pointed here, but the flash is going off over there. Analogous to FRBs, 1,000 FRBs go off, every day, but we only discovered them recently because we just happen to have the telescope pointed to the right place at the right time. So if you want to look for rare pulses, it's good to cover a wide field of view. So this is kind of exploring a new phase space where we're increasing the field of view by a factor of about 100,000 and looking at hundreds of millions of stars simultaneously for these nanosecond or millisecond or microsecond pulses. So in order to do this, we need to build a lot of cheap telescopes and point them in different directions. And so one of the solutions was to use a plastic lens, a Fresnel lens. These are really cheap. They cost $50 or $100. These are 18 inches, half meter across. And they're not as good as glass lenses, but we're just using them as light buckets just to collect the light. We don't need really sharp images, so they work beautifully. Another really important technology that just came out in the last 2 years is cheap detectors that work at nanosecond timescales. They're called MPPCs, multi-pixel photon counting detectors, or silicon avalanche photodiode arrays. There are some in the infrared, there's some in the visible. They have high quantum efficiency, and you can get them arrayed. And they're very linear. So you can see a set of pulses these are single photon events. Here's one that's 2 photons. Here's one that's 3 photons. It's easy to tell whether it's a 1, 2, 3, or 4, or 10 photons are hitting you simultaneously. The reason they're cheap, they're $5 a pixel, is because they're used in positron emission tomography for medical imaging, where they surround your body with these detectors to detect cancer. So we want to build this thing that can look at many places at once. And we want to have a couple of observatories in each location. And we designed a lot of the electronics. It's working well. This is a board with a Kintex 7 FPGA, a couple of ASICs that do a lot of analog stuff. On the back are a bunch of these detectors. And this is what it looks like in the focal plane. There's 4 of these boards, and here are the detectors, which is 1,024 of these pixels. We use this white rabbit technology to do time and frequency transfer, because we want to know exactly when these pulses arrive at our telescope to sort of nanosecond precision. White rabbit, you can get something like 30 picosecond time transfer over internet. So it's a good way to distribute the kind of usual way in Casper is to have a couple of coaxes with 1 PPS and 10 or 100 megahertz. I recommend White Rabbit. You do have to put a little circuit on your board that costs about $50, $25 in parts. There is a way to do it without hardware added to the board, but it's proprietary. If you add the $25 in parts circuit, it's a pretty simple little VCO circuit and a DAC. And then it's open source gateware and software. But if you use this technique without the chips, then it's proprietary. It belongs to 7 Solutions, and you have to pay them to do that. But if you're designing a board, I recommend you add this White Rabbit capability. So we've got a prototype system. We don't have the thing with lots of telescopes poking out in all directions, but we deployed this thing. Each telescope covers 100 square degrees at 10 by 10 field of view. We deployed this thing at Lick, very fortunate, just before COVID broke out. So we've been able to observe for more than a year now in our pajamas. The end goal is to build something that looks like this. This is artist's conception of a dome that has several dozen telescopes poking out. Each one of these is a half-meter telescope with a few FPGAs behind it. And actually to have two domes separated by 1 kilometer apart, because there is an atmospheric phenomena that generates flashes that we need to discriminate against. It's called Cherenkov radiation. When a high energy particle comes into the atmosphere, it can make a flash of light, and we need to do that parallax measurement, triangulate, measure the timing. And we can do that. We've demonstrated that at Palomar with a couple of telescopes separated a kilometer. So we're in the kind of production, we're learning how to scale this thing up right now. This is our production telescope. This is our dome design. We don't have this thing yet. We've got our site selected at Palomar, where it'll be our first place. We might put one on the other side of the Earth too, so we can cover even more of the sky. What I'm excited about is that we're covering a whole new search space here that's largely been unexplored. This search space from sort of sub-nanosecond flashes to microsecond to millisecond up to about a second is largely unexplored. And what's interesting, so when you get above a second, when you get above a second, then other telescopes are pretty good at that, although not as wide field. They use CCD cameras and they integrate for seconds to minutes. But if you're looking for short pulses, PANOSETI is going to be the thing. What's interesting about exploring a new phase space is that whenever astronomers look at some new wavelength space or new size scale, or in this case, new time scale, nature seems to populate that phase space with phenomena. And so there's a good way to make a discovery is just look at some place that nobody's looked at before. And we don't understand why nature just populates all size scales and time scales and wavelength scales with phenomena. We understand why that's true in evolution and life. If there's some new biological niche, creatures will evolve to be there, but we don't understand why in nature that happens. So we might find something interesting. A couple of my favorite quotes: SETI is the archaeology of the future. That's from Phil Morrison, saying that if we ever find ET, it's likely they're going to be billions of years ahead of us. You know, our sun is sort of middle-aged, but a lot of stars are 10 billion years old, twice as old as we are. And that means we'll get on the galactic internet, we'll learn all their music, poetry, science, literature, and how they got through their bottleneck and stopped killing each other. So there's a lot we can learn. Carl Sagan said that SETI is profound either way. And I think what he meant by that was that if we do get on the galactic internet, we can learn a lot. But it's also profound if we can do a thorough search, maybe in 50 or 100 years, and look at a lot of different signal types, a lot of wavelengths, and we don't see anything. That means that life, intelligent life, is incredibly rare. We better take really good care of life on this planet. Finally, I wanted to end up with a couple of haikus. So the SETI at Home participants help us, and they built one of the largest supercomputers on the planet, made the most sensitive search ever in SETI possible, and they send money, they write the code, it's open source, but they also compose poems. And so I'll just read you a couple of haikus that people have sent us. Dan Seidner: 1 million Earthlings, bounded by optimism, leave their PCs on. And Paula Cook at Duke University: searching for life, answers are revealed about ourselves. So thanks very much. And I want to thank Catherine and Ryan and Melissa, who have been doing a lot of work to organize this conference. Thank you.
Thank you. That was a great talk. And we have a couple questions in the chat from Lincoln. For laser communications over long distances, pointing and stability becomes more difficult. Does this affect the practicality for alien users?
Yeah, so I think that aliens that are worth their salt, you know, that are, I don't know, maybe 1 billion years ahead of us will probably know how to do that. Well, we already have, you know, pretty good pointing techniques where we can do that. I think if they're nearby, you don't want to use a really directed laser. You might want to fuzz out the beam, but if they're far away, then you can just let it go. One problem though is that we don't know the distances to the planets very well, exoplanets. So if you're going to have a really tight beam, You have to know where the planet is in the orbit. So you have to measure distances fairly carefully. But ET, I think, will know how to do that.
And then another question, how would you differentiate a prospective SETI signal from the host star's flare signature in the optical or infrared? This is from Harihar and Krishnan.
Yeah, so I think flares are on a very different time scale. My understanding, I'm not an expert on flares, but my understanding is that they evolve over minutes or hours. And we are not really sensitive to those long time scales. We're looking for sort of millisecond, microsecond events. We can't really even detect flares.
And another question from Lincoln, are laser arrays such as Starshot a way forward for billion-year ahead aliens?
Yeah, so so Starshot is a sort of a mission that people are thinking about with a laser sail where the laser's on the ground, and it's got a very powerful laser to push the spacecraft to a nearby star, Proxima Centauri, and get there really fast, traveling at 20% the speed of light. Yeah, we could detect those kind of lasers, probably not with it's probably not a pulse laser, it's probably a continuous laser. So there are other work going on at Berkeley doing spectroscopy, looking for narrow band lasers, continuous lasers. And those things we could detect on the other side of the galaxy as well, but not so well with PANOSETI.
And then I had one question, can you do PANOSETI, or maybe, I guess it wouldn't be quite panoptic, but can you do SETI piggybacking on existing Cherenkov experiments that are studying cosmic rays?
Well, in fact, we're working with people that do precisely that. And there's a group at Veritas that has, and the beautiful thing that you may know, Catherine, but these telescopes are huge. This thing is the 12-meter telescope, and they've adapted it to look for these pulses. And it's mostly a targeted thing. It's not one of these all sky thing, but they're very sensitive, and it's a good idea. And people are starting to think about how to do that better.
Well, thank you for that talk, and let's move on to the next speaker in the session, who is Kaushal from the Giant Meter Wave Radio Telescope Observatory.
Hi, thanks, Catherine. Am I audible? Am I audible? And are my slides visible on the screen?
Sounds good, and the slide looks good.
Yeah, thanks. So today, on behalf of my team at GMRT, I will be talking about the recent updates from the real-time RFI mitigation system of the upgraded GMRT. So the upgraded GMRT, which has been operational since 2019, has 4 observing bands. A band 2, which goes from 120 to 240 megahertz, band 3, which goes from 250 to 500, band 4, which goes from 550 to 850, and then band 5, or the L band, which goes from 1050 to 1450 megahertz. The maximum receiver bandwidth is 400 megahertz, and the backend processing is carried out using 16 Roach1 boards, which feed the data after digitization and RFI filtering to the CPU GPU cluster, which is a 16 node cluster. So today I'll talk about the broadband power line RFI at GMRT and our efforts to mitigate it. So the major cause of this broadband or impulsive interference due to sparking on power lines, basically gap discharge on high voltage transmission lines and distribution equipment like transformers and faulty joints and dangling wires, is mostly seen below 800 megahertz, but it's a very prominent source of interference at these frequencies. So here is an example, oscilloscope trace of about 50 millisecond. The first one, the topmost, is taken in band 2, and band 3, band 4, and band 5. This is simultaneously acquired using a 4-channel oscilloscope from 4 nearby antennas. So you can see that the RFI is all the way up to the last band, that is just up to band 4 of GMRT. And its strength varies. It is strongest in band 2, and then it goes on, the strength goes on reducing. So the algorithm which we use is a robust estimator which estimates the dispersion of the signal. So we take time samples coming right away from the ADC, and generally, since these are all median based estimators, so we should take twice the duration of RFI as the window size. Once this is done, we compute median absolute deviation through the formula which is mentioned in this top left box. And once, so it has 2 median computations, and then the robust threshold is estimated as median plus minus n times the sigma, which is calculated through median absolute deviation, or MAD. Once this is done, each sample is compared with the threshold, and if the sample is outside the threshold, it is replaced by a constant value or noise, or it is clipped. That means it's replaced by the threshold. Now this works well, but if there are longer bursts of RFI and if the hardware isn't able to support, for that we have come up with a solution where we hold these median absolute deviation values in a buffer, and we do this successively, and then we take the median of these MAD values. We call it median of MAD or MOM. And this is a hardware optimized solution. With this, we are able to take care of the longer duration bursts of interference. And as an example, on the right, we have 2 plots. So these are emulated RFI signals from pulse noise, analog pulse noise source, which are fed to the RFI filter. And the top one is filtered using median absolute deviation. So one can see that when the red colored bursts are longer than twice the size of the RFI which the algorithm can handle, then it's not able to completely filter. Whereas the bottom one is the same signal but is filtered through median of MAD algorithms. It is able to filter it properly. So the way it was implemented on Roach is that the input data, the top left box, the input data is what comes from the ADC, digitized samples onto FPGA. First, the estimation is done and standard deviation is calculated through robust statistics, and subsequently the threshold is calculated, and then the detection happens and replacement of these samples with the desired values happens. In the meantime, the data is also buffered while this is going on. While this process is going on, because we need the original data back for replacement. And so one can see that this data comes out from the 10 gigabit Ethernet port on Roach 1, and this goes to the CPU GPU cluster for further processing. However, we also have an RFI counter which counts the total number of instances that have passed in a certain duration, and also the number of samples flagged, so that we can give the percentage fraction of RFI for each antenna and polarization. So here you see this after processing, the bar chart on the left. This shows for each antenna what was the percentage of RFI flagged in a certain duration. All of this is controlled in real time from the GMRT control room through a GUI, the left corner, and this is controlled through the usual 1 GB link and through the Python scripts which control the Roach. So this is fully operational, and it is used for the GMRT observations. So how did we test while it was under development? So the technique we have used is the simultaneous testing. So what is done is, since we want to know exactly what happened to the data with the filter and without the filter, so what is being done is the input is split digitally inside the FPGA, and one copy of the input goes without filtering, whereas one goes with the filter. And the correlator delay is balanced in such a way that the correlator treats the signal as if it's coming from the same antenna. So we can do a fair comparison. So here is a small frequency versus time spectrogram. X-axis is frequency, Y is time of a beamformer output, which is approximately 81 microsecond time resolution. And about 50 millisecond sample is plotted here. The top one, which comes without the filter through the beamformer, one can see the horizontal lines which are repeated repeating at 10 milliseconds. This is because the power line RFI goes in multiples of the power line frequency. So it's 50 hertz in India. So it's 20 millisecond period. So it sparks twice in one cycle. So we usually get 10 milliseconds. So here you can see this broad stripes repeating every 10 milliseconds on the top plot. And the same through unfiltered is completely removed. So this signature is removed in this. Now to analyze further about the mitigation of power line RFI. So usually, since the RFI is broadband, we prefer analyzing one spectral channel over time. So this is one spectral channel corresponding to 451 megahertz, the top plot. It's actually a beamformer output of a single antenna. It's power as a function of time. And one can see the red ones are the, due to power and RFI, the high power values you can see here. And then it is removed in the, as can be seen in the blue colored plot. This is all 3 sigma filtering, and we are replacing the samples by digital noise. So if we take the Fourier transform of this, we can see the periodicity in the upper first plot, whatever time series we saw. So in the bottom plot is the magnitude spectrum, and one can see 50 hertz and its harmonics on the x-axis, and the power in each of these for unfiltered in red, and the filtered one simultaneously. One can see that it is removed almost by a factor of 6 dB or so. So that's the kind of rejection we get. Now, most of this power line RFI is spatially correlated. So the correlation peaks in nearby antennas due to power line RFI. So this is one plot. This is UV amplitude as a function of baseline length, taken again in the digital copy mode, where the antennas are recorded with unfiltered as well as filtered. And this is for a point source. So ideally, the cross correlation should remain same across all the baselines. As can be seen in the red highlighted circle in the unfiltered plot in the left, we can see that at wavelengths, at baseline lengths less than 4 kilo lambda, which is approximately 2 kilometers, one can see the increase in the the scatter of the UV amplitude, and which is removed to a significant extent in the plot towards the right for the same UV lens. Whereas you can see that the baselines above 12 kilo lambda are unaltered. So if we look at imaging for extended source, because this example is specifically put because we know that broadband RFI or this kind of RFI affects more short baselines. So this is an extragalactic field, and this again a test observation. So one can see simultaneously unfiltered and filtered. So this is again the image to bring out the effects. The image is made for baselines less than 1 kilo lambda, that is about half a kilometer. And the noise RMS as measured for unfiltered is 1.6 millijansky per beam, and after filtering the noise RMS is 0.52 millijansky per beam. So there's approximately a factor of 3 improvement in the noise RMS. Coming to an example of time domain astronomy, the J0418 minus 4154 pulsar was observed through this, and this is about I think 14 antennas were used in this observation in the incoherent array mode, and one can see that there is a SNR improvement in the filtered over unfiltered by a factor of about 3. So to summarize, real-time broadband RFI filtering is operational on the GMRT wideband backend or GWB, and so far the tests which we have done shows an improvement about 4 to 6 dB in the SNR, and imaging performance is also found to be improved. The typical flagging percentage at 3 sigma threshold varies again from in different bands and different times of the year. So it varies from 0.5% to about 5%. And this system is released on a shared risk basis for the upgraded GMRT users, and since about a year or so. Currently, we are working towards schemes for propagating RFI flags through the backend system. So the current way is only through counters where we can record the fraction of RFI, but we would like to go for slightly more sophisticated schemes of bookkeeping of RFI. And while we do this, we are also refining the filtering technique to take care of lower level RFI and improve the performance of filtering. Yeah, thank you.
Thank you. There's a question in the chat, maybe a couple questions, and since we started a couple minutes late, I'll go a couple minutes late and just postpone the break. So Lincoln is asking, is there a risk that replacement of bad values in the MAD implementation will skew noise statistics? And then there was some discussion in the chat about that.
Sorry, I couldn't get the question.
The question was whether replacing bad values will skew noise statistics. And then there was also some discussion about whether that would happen.
Sorry, I think my internet connection went off in between. Can you? I can check the chat probably.
Okay, yeah. Maybe we should move on to the next speaker now, and we can continue this discussion in the on Slack, because there are a few statistics questions about this, and I also had a question that I wanted to ask, but I'll just ask it in the Slack.
Yeah, fine.
So before the break, we're going to add in the Sparkler talk that was missed on Monday. And so we'll just play Histik Grobler's talk now.
Good day, everyone. My name is Histik Grobler. I'm a final year engineering master student from the University of Johannesburg. My supervisor from UJ is Prof. Swart. Co-supervisor from Sarel Hartbees Hoekstad is Dr. Fani van den Neever. I'm investigating if a radiometer with 4 spectral windows can be implemented on a single FPGA board, specifically a Roach 2-based system. The system is going to be implemented at the Hartbeespoort Radio Astronomy Observatory that forms part of the South African Radio Astronomy Observatory and is located in Hartbeespoort, just outside of Johannesburg. The system is a normal radiometer. We can do continuum observations, but it has 4 tunable movable windows inside the main bandwidth that can be moved up and down inside a bandwidth with 1 megahertz windows. This is an overview of the system that gets digitized by the ADC, goes to the windowing system, pass through filters, and we get our output. Here we can see a 2 millihertz signal with noise as input. And the output, we can see it has been shifted around 17 millihertz and the noise has been cancelled. Thank you, and you're more than welcome to ask questions.
Okay, I think we're going to start our break now, but if anyone wants to stick around and ask a question, we have time for a question or two. But our next talk will be at 9:15 from Intel. Hi all, it's 9:15, so we're ready to get started, but I'm not sure if our speaker from Intel is here yet. I know he was coming from a meeting at the last minute, and so if Bill, are you here? Okay, we can maybe wait a few more minutes, but the next talk will be an invited talk from Intel. So I guess a couple announcements in the meantime. After this talk, we're going to have 2 breakout discussions that are in parallel. One will be on documentation and one will be on RFI. And so if you go back to the links that are in the Slack and also in the email I sent, this RFI session is what the other Zoom link is for. And the documentation session will stay in this main Zoom. And then after that, we'll come back to the main Zoom for a closing talk that Amish is going to give, where he'll sum up what happened this week and give some remarks about looking forward to next things that Casper will be doing. And Amish has probably been asking the people who've taken notes in discussion sessions to send along highlights and notes. I don't know if I saw that you unmuted. I don't know if you had any more to request about that.
No, I was just agreeing with you. Yes.
Sounds good. Okay, and Ryan has asked me to give a reminder that all of the live streams are going directly to YouTube unless you've asked us to not record your talk, and then the recording is to a private YouTube so that it can be taken out before it gets posted. So if you've requested for your talk not to be online, then it's been removed. But if you haven't specifically requested, it'll be on YouTube. So just let me know if you don't want that.
Catherine, is there a place where there's links to all the talks?
Yes, on the website, on the agenda page, there's links to a YouTube channel, and then if you click on that link, there will be separate talks, which for now I think they're just broken down by session or by day. But a little later we might be able to get links to specific talks. But if you know when a talk was in the schedule, you can just fast forward to that part of the recording.
Thanks.
The talks are also broken down in the videos. So if you would go to the description, there should be markers for when each talk has start. So if you want to go to a specific talk, you can click on that. And the title and the speaker for the talk matches directly with the agenda item on the web page.
Awesome.
Catherine, apologies for chipping in. Bill is struggling to join. Says something similar that we've had before, that it's asking for email and password. Is there any tips I can give him for getting in?
I think he just needs to be logged into a Zoom account.
Yeah, so he just, for all participants, they need to be logged into a verified Zoom account. Zoom might require people to verify their emails or something like that. But as long as they're logged into their Zoom account, they should be able to join this workshop. So if there's any issue, just let me know and I can try to work with them to get them in here.
Okay, I just passed that on. I will see what happens. Just give us another minute.
And yeah, he can make a free personal account. It doesn't have to be linked to his organization.
We have a minute. Is there a place to upload our talks, the slides?
Yeah, so originally we were just going to upload the recordings, but a few people have asked about slides, so I'll probably make another folder in the workshop Google Drive. I think that would be the easiest way, but I haven't set that up yet. So I guess watch for an email after this session.
Thanks. Where can I find a link to the Google Drive?
There's a link to the folder for recordings of presentations, but I could make a new folder for PDFs.
Okay, it's all in the same place as the recorded submissions.
Yeah, that would also be fine.
Great.
Francois, is there any news from Bill?
He is trying. Latest is that he's struggling to create a Zoom account. So I'm not sure, that must be a restriction on his side. So perhaps he could use some different network address or something.
Does he need to create an account? Can he just use Google credentials? Do you know? I thought if he just logs in as a Gmail address, it might be able to just.
Sorry, I'm in now.
Excellent.
Sorry, I don't know why that was so hard. It wouldn't let me. I had to create a whole new account. So I did, and I apologize.
Thank you very much for putting up with that, and I'm glad that you made it in. Do you want to go ahead and share your slides?
Yeah, you tell me when and if you can see them. I don't think it's shared. Let me try that again. Are you guys able to see it or no?
Not yet. So if you click screen share, then it will ask you which app or screen, and so then you'll select that and then click share again.
Oh, maybe that's what I did. I missed the share part. How do I unshare?
I think you click share screen again and you can unshare.
So I'm not seeing anything is the problem.
We just see a black screen.
Here, let me do it this way. All right, let me kill that. Share screen. I apologize. I've never used Zoom, so it's my first time using it. Share. There we go. That's better.
That looks good.
Great.
Okay, I'll make it big. I apologize. That should not have been this hard. You'd think I'd be a pro by now by all these things that we have to use. So let me dive in. I'm Bill Jenkins with Intel. I'm part of our programmable solutions group, which is what is the FPGA team. One of the things I do, a lot of different things. I'm a HPC architect, but I also do a lot of business development for our military, aerospace, and government business unit. So kind of the things I'm going to talk to you about today are kind of fundamental to what we are doing at Intel, not just in our FPGAs, but our products as a whole. I tend to focus on FPGAs, but it's really well more than just we build products that people can buy and sell, especially silicon. We are partnered, and a lot of the work I've worked on over the past 2 or 3 years has partnered us with the US government. And hopefully we can continue to partner with other governments around this concept of heterogeneous packaging. And fundamentally, I'll explain what all that means. I'm not going to get into our parts, our FPGA parts. What I kind of wanted to do is just showcase previously with our older devices, Max, Cyclone, and Aria, and our previous Stratix 5 devices. Those were all built at TSMC. When we moved to Intel's Foundry with Stratix 10 and now Agilex, what I'm going to show you is the fundamental thing that we did that changes, basically the premise behind what we're going to talk to you about. So we now have a partnership with the U.S. government, and as I said before, I am working with other nations to form similar agreements. It's around microelectronics assurance, which is, again, the word assurance has replaced the term of trusted. And there's really 3 components to this, and this is probably a little less important for what you need, but it's the fundamental backbone, which you need to know, but fundamental backbone behind a lot of the things that and what are driving what we're doing, which I think will be very interesting to you. So there's 3 aspects to this. When you build, the first part is what we call RAMP, or Rapid Assured Microelectronics Prototypes. And that's when I build an ASIC, when I build a device, a semiconductor chip. How do I know that what I designed is what I got, that it wasn't counterfeited, that it wasn't touched or manipulated in any way, backdoors put in, malicious hardware inserted? So in my space, but also I would argue that in every space, this is a problem, and it's growing interest. And so in my space, the military, aerospace, and government business unit, this is paramount. So Microsoft won the RAMP contract from the government. They use our PDK for Intel Foundry. So what I mean by that is Intel has a foundry. We produce semiconductors, devices, and the government is now working with us and Microsoft, and we're actually the lead on what's called RAMP-C as well, which is kind of the next evolution of this, for the objective of building devices that are protected. They're secure, they're encrypted, they can be built in non-secure or ITAR facilities, and so therefore you are knowing that the device you're putting on a board and the putting in a system is the device that you purchased, is the device that was designed by the manufacturer. I'll talk a little bit about Foundry at the end too, because this all does kind of tie together. But effectively, the short of it is that Intel has foundries all over the world. And so part of the partnerships I'm trying to build with governments is that things can be made in their local area. So throughout Europe, different places throughout Asia, North America, lots of locations. The third piece, which is the focus of what I wanted to talk to you about, is what we call SHIP, which is state-of-the-art heterogeneous integrated packaging. And we were granted this last year from the U.S. government, and this very specifically is about building what we call multi-chip packages. So what we do at Intel, and what I'll kind of explain, is this is how we build our parts today, but this has a huge impact to the future of electronics and system design. We're able to shrink systems down by orders of magnitude, 8 to 10x smaller. So it's all about size, weight, power, and cost. And so this was granted. The kind of the phase that we're in now is proof of concepts. Let's build some prototypes for the defense industrial base to show that we can take devices, die from different vendors, and stitch them together into a multi-chip package. The next phase will be productization, and then infrastructure and scale. So over the next 5 to 7 years, you may have heard of some of the things going on, maybe not, but our new CEO, this is probably work we've had going with 3 or 4 years with our previous CEO and the previous administration, President Trump. And this has continued with President Biden, where our new CEO has a partnership with the US government. They just approved a big act to try to promote this kind of thing. My effort is to replicate what we're doing here kind of throughout the globe, to offer this kind of leading edge technology to other nations. And these are the kind of architectures that we're trying to build with SHIP, which is some form of RF front end, some inline compute accelerator connected to an FPGA with transceivers on the back end at its simplest view. So let me explain what that all means. So one of the things that we do at Intel, as I said before, previously we were built the way everybody else builds products. Drop an FPGA, monolithic FPGA die on a substrate. What we created at Intel with our 14 nanometer technology is heterogeneous packaging. Effectively, it takes and the die and separates the functionalities of the different pieces of that die, breaks it apart. So we still have a monolithic FPGA fabric, but our transceivers are now disconnected from the FPGA. And those tiles, those chiplets or ASIC die for those transceivers are connected over what we call the embedded multi-die interconnect bridge, or EMIB. And why that's important is because these interconnects are very, very fast, and I'll show you they're very fast, very low power, very low latency, and very small. So we're able to do basically thousands of connections between those die in a very efficient way. So today, we get about a terabit per second of full bandwidth, full duplex bandwidth across those interconnects. And so that's proprietary to how Intel builds its parts. What the government wanted us to do was create an open protocol, something we call AIB, Advanced Interconnect Bridge, which defines a transactional protocol between die, between those chiplets. And so this is an open standard that really is a method for communicating. Today we're at AIB 1.0, which is a terabit per second over EMIB. It's not bound by the underlying connection. So if we use EMIB, if we use silicon interconnects or any other method of connecting die together in a package, it'll work. But the benefit of AIB over EMIB especially is performance. And performance in the concept of power. So when you're connecting these RF tiles through SerDes or JESD, typically you're at about 17 picojoules per bit. With AIB 1.0, we're at 0.85 picojoules per bit. So about a 17th the power. And better latency response to about a 10th of latency, maybe a little better than that. And the benefit here too is we're introducing AIB 2.0, which has 4 times the bandwidth. So again, terabit per second, you're going to quadruple that. And that actually lowers the power per bit to about 0.5 or 0.47 picojoules per bit. So if you look at that, right, it's all about thousands of wires interconnecting these things together. I'm able to, compared to a discrete solution or a traditional way that people build chips, this is going to give you a significant power savings, on the order of between 17 and 35x the power. So significant. And so a lot of what we did from our CTO office was kind of prove this concept out beyond just our own parts. So we built a program called Pipes. We built an optical tile. So a lot of what you're going to hear me talk about is this ecosystem of these chiplets or die or tiles. So we built an optical tile. So with this optical tile, we bring fiber optics directly into the FPGA. So no external transceivers, no external cages, fiber directly into the FPGA. And through the SHIP program I talked about earlier, part of what we're working on through that program is to find a ruggedized method of connecting those optics directly in package. So what this proved was I could take our new, again, this was several years ago, our new, at that time, Stratix 10 14 nanometer FPGA that has 6 AIB ports on it and connect 6 optical tiles. So think optical tiles, think multi-terabytes per second over multiple kilometers of distance, those kinds of numbers. So we created one that had 6 of them in. Yes, that worked. We were able to build a device with multiple of these things connected, proved out AIB, proved out the chiplet building concept. That was then further evolved to another program called CHIPS, where we added a digital front end, RF front end, so A to D, D to A. This is a 64 gigasample, 32 gigahertz converter. I'll talk about that in just a little bit. We have 2 of them on this package. We have an AI accelerator that sits on this package. We have 2 of those optical tiles and a transceiver. So this was, again, can I take tiles, die, right, from different vendors, from different technology nodes, add AIB to it, and then build a chip heterogeneously with those different components, right? So this became the prototype platform for what we call our direct RF line, which I'll talk about, as I said. And then the other piece was then, can I take that one step further and have the defense industrial base, who's been, really in my group, we're driving a lot of this effort between the government and the defense industry. But effectively, commercialization is where we're heading for all this, not only on our own products, but again, for commercial companies as well. So what we did is we said, okay, well, Intel has a foundry. Let's offer you a spot to build an ASIC for free, funded by the government, add AIB to it, and connect that up to our direct RF component, so to do kind of some pre-processing. And this heterogeneous integration effort is what became the prototype for SHIP, for this SHIP concept, and that was several years ago. So what we're doing now, and what the effort is as we scale this up, so again, what we did is we're building prototypes of this concept now. We're going to build a business model around it. So to make this successful long term is to build an ecosystem of these chiplets that are that have AIB on them. So we're looking for things like other digital converter tiles. So we're working with Analog Devices and TI and third parties and within Intel directly to add AIB to a number of different converter tiles. We're building, I think we have 3 variants of the optical tile that we're looking at. Which one do we actually productize? Intel obviously is a processor company as well. So Xeons like Ice Lake D and others, can I put those in package? Atoms as well, can I connect those up in package to other things? As we make custom ASICs, we call this dense compute. So there's things that we're working on that are 12 to 20x the performance per watt of an FPGA that are reconfigurable in a half a second, but give you that performance per watt density that you need as an acceleration ASIC. And so there's things like that we're working on that tie into this chiplet ecosystem. But then what other things do people want to see connected? And again, as I said, this is how we build our parts. So when we were building our Stratix 10 14 nanometer device, we replaced that FPGA fabric with the Agile X, we call it, the 10 nanometer device, and it just worked, right? So we've been very impressed and proud by how well this, we paid our dues. It was like buying the first year model of a car with Stratix 10. With Agile X, it really, there was no errata, it just worked. We had all existing tiles that we knew worked because from the previous devices, the previous packages, we just were dropped in the new fabric and it connected up and everything worked. So the goal now is to build out that ecosystem of other things that people want connected to the FPGA or to each other, and kind of expand that. And that's the premise behind what we're doing with SHIP. And just to kind of give you a snapshot, some of the tiles we have are H tile, E tile, P tile. So think of different transceiver speeds. Some have PCI Express, some have Ethernet and with hard max and FEX. The F tile is the newest one that goes up to 116 gig with 400 gig max and FEX and PCI Gen 4. And then the R tile adds PCI Gen 5 by 16 with a CXL interface. So our cache coherent interface to the processor. So now we can be an direct extension to the cache of the CPU, connecting through this R tile. So again, these are just some of the tiles that our own devices, FPGAs and CPUs use. So as I said earlier, the device that I know you guys are familiar with on certainly on the Xilinx side, but may not be as familiar with what we're doing on the Intel side, because effectively we're not allowed to talk about it. And we're not allowed to talk about it because the device, beyond what I'm going to tell you today, is because we have a whole product line of direct RF FPGAs, but it all came from some of the government funded work and what we're doing with SHIP to leverage those heterogeneous packaging concepts. So the first device that we have today that's been in use for about a year and a half. It's a gap in the market. It wasn't just to go fill the market with what everyone else can do. It was to really build something that was solving a problem that no one else had solved. So we built this device. It's a Stratix 10 with 2 of these. We call them A tiles. So each has 4 transmit and 4 receive pairs, each tile. So one device has 8 transmit and 8 receive. It removes a lot of the analog circuitry on the board. So we're seeing about about an 8x or 1/8 the size of a discrete implementation at a fraction of the power and about 1/10 the cost. And these are 64 gigasample parts. So, again, given the bandwidth required to get that kind of data from one device to another, using thousands of very high speed again, not SerDes, but signaling. One of these is 64 gigasamples, and you can look at pretty much the whole 32 gigahertz spectrum with one of them, and use the other one to say have 16 channels at 500 megahertz around a particular band. And 2 clock cycles later, right, a few nanoseconds later, move that from 4 gigahertz to 8 gigahertz. And that's what we call real-time frequency agility. It's interpretable, or sorry, not interpretable. You can interpolate down effectively by up to 1024. So while you can look at the whole spectrum, you can also look at a very small slice of the spectrum. And by doing that, you get more channels effectively, because again, we have a lot of bandwidth, but it's not using SerDes or JESD. And there's a follow-on device, that small form factor version. It's basically half the size, that uses our Agile-X device. And the power behind that is that there's nothing out there that can do that. So because of that, the government and some of the defense industrial base wanted exclusivity, so we didn't come to market with this openly. So we have a plethora of products kind of following suit behind this, using different companies' tiles through our partnership with, as I said, that ecosystem. So over the next 2 or 3 years, you're going to see, and through the SHIP effort, as we build generic platforms through SHIP. Again, maybe I'll jump to this slide to kind of show that. The idea is that we're going to have a whole bunch of new parts coming around that have those kinds of architectures, because what the government wants to see in the US is an ecosystem of these things. And so what we're trying to do is partner with other countries to do this kind of heterogeneous packaging in the UK and Germany and in Italy and Israel and all the different places throughout Europe and Asia and stuff, that where we have facilities that have this capability. To leverage what we're doing at Intel, to leverage the technologies that we have at Intel that we build our products with, and what we're doing here for the defense industrial base, to scale that to a commercial application, to scale it to a business model that everyone can take advantage of. And from that, we're going to see over the next 3 to 5 years, kind of I want to call an accelerated product development cycle, because we're going to see so many things coming out of these SHIP efforts, things that have lots of types of embedded memory. Not only DRAM, flash, Optane memory, HBM, but even MAX devices, even power in package, different types of transceiver interconnects, eASIC and ASICs connected both inline and as sidecar accelerators, as kind of the objective. And these kinds of things, as I talked about earlier, where you have an A to D, right, your RF front end and an FPGA, a lot of people want to pull out some of that pre-processing into an ASIC or an eASIC device, where they can really lower the power on these things that they do a lot of, even shrink the size of the FPGA, or just keep the FPGA the same size and add more compute on the back end. So you're going to start to see these kinds of variations coming over the next few years from us too, through this SHIP effort. As we kind of figure out what people want and what people are going to build themselves, and we productize all that. So all of this is what SHIP is really providing us, that heterogeneous packaging capability. And to tie it kind of together, right, FPGAs have their place. They will always have their place. Reprogrammability is key. ASICs also have their place, but the problem with ASICs is they're expensive. You typically need large volume to offset that expense, and they take a while to develop. So we acquired a company called eASIC, which is a structured ASIC. So think of it as the balance between a custom ASIC or an FPGA, where you don't have the reprogrammability, but you don't have the cost or development time of an ASIC. So where an ASIC might be tens of millions of US dollars, 50, 60, even $100 million, an eASIC could be 3 to 5, 1 to 3 million. And where you have multiple years of development time with an ASIC, it's about a 9-week turnaround for an eASIC device with our next generation devices. And why I'm saying that is twofold, really, again, without getting into too much detail, and I probably already have. All we really do is it's a higher level abstraction of an FPGA. So we build not all the way from standard cell ASICs, but we build it with bigger building blocks. And we remove those reprogrammable layers of the FPGA with via mask layers. So those metal layers get hardened effectively in an eASIC device. So you get typically an eighth to a tenth the power, and even a doubling of performance over an FPGA in many cases. And I won't go through all of this stuff. I only have a couple more slides, and I want to try to wrap up on time. I know this is probably the last presentation. So you pick the devices just like you would an FPGA. How many resources, how many transceivers and things like that. And there's even a path to, and again, it doesn't have to just be Intel, right? Can be Microsemi, can be Xilinx, whomever. We have a path to eASIC. We have a path either from FPGA or eASIC to ASIC. Very quickly, kind of similar to what we used to do before with hard copy. And the intention of all of this is to leverage local governments, local Intel facilities to leverage our state-of-the-art technology to build these devices, and then take those die, those chiplets, and incorporate them into multi-chip packages. So we can drastically reduce the size, weight, power, and cost of systems. And so today for Intel Foundry, we have our 14 nanometer PDK, which we actually call 22 FFL. 7 nanometer is what we're using in the ramp programs, which I think 7 nanometer would be equivalent to a TSMC 5. And so that's available through the ramp program, and that will eventually be available to the public within the next couple of years. But 22 FFL is very well established. And so all of that kind of ties together, as I said before. I think that's my last slide. Let me stop there. And I guess if I have time for questions, great. If not, I understand I was pretty late starting. I know that was a lot and very fast.
Thank you for that talk. I think we do have time for a question or two. Francois asks in the chat, are the AIB mechanics also open and standardized? Would it be possible for a third-party vendor to design a chiplet to integrate into the same space?
Yeah, sorry. So when I said open, that's exactly what I meant. So the standard is public. The link is here to it. It's on the GitHub. That's exactly the point. Some of our own die, we have people, I think there's at least 3 people that we've worked with who have actually built AIB RTL, right, for the FPGA. That's available to other people building ASICs, so that they have RTL available. They can start with that, or they can do it themselves if they so choose. But there's at least 2, if not 3, companies with RTL available for AIB today, but it's an open standard. That is exactly the intention, is to make AIB as an open standard to allow integration and adoption of the ecosystem.
Great. And the other question is, are the ADCs interleaved?
They can be. They are not. The objective is to get to full digital, but they can be or they cannot be. We have, it's not, because of the AIB bandwidth, we're not bound to force interleaving. We have 4 independent channels. What I will say is, to get 64 gigasamples, we only effectively use 1 of the transmit and receive channels. So with AIB 2.0, which is 4 times more, kind of the next generation of parts we're going to be releasing, we'll actually, one of those devices would have 8 of those 64 gigasample or 64 gig, parts, would have 8 channels, and therefore 8 ports. And so theoretically, people could have interleaved, you could have 128 gigasample, or you could have 8 64 gigasample paths. But that's the idea of it, is because of AIB, we're not bound by or forced to interleave.
Thank you again for your talk. So now there's going to be a documentation discussion in this Zoom room. Anyone who's interested in that, stay here. And anyone who wants to go to the RFI discussion, click on the other link that is pinned in the Slack and also in the emails I sent earlier. I'm going to move over to the RFI room.
Okay, thank you, everybody.
Okay, I guess I can just get started on the documentation discussion. This probably isn't going to be the most interesting of discussions that have been held this week. Documentation rarely is, but unfortunately it is necessary. So I'm just going to share my screen. A few things on the agenda that I've thought of are what documentation updates need to be done, and then can we maybe implement a better method of updating documentations that isn't just sending me random emails that I inevitably forget about to add things into the documentation. Is there anything else anybody thinks needs to be discussed? No?
I think it's going to take
Okay.
a minute for everyone to collect their thoughts.
Sure. Well, let me know.
So I think, let's see, I mean, the read the docs does need to be kept up to date, as you've listed there, Casper FPGA, as Python versions change and things like that, we need to make sure that's all kept up to date. I'm also thinking, though, that the blocks themselves are still severely lacking in documentation.
Yeah.
So I think updates to those blocks could be useful, because even those that have blocks are often unclear on the specifics of some things about.
Yeah, and there's a whole lot of blocks that are missing.
Yeah. So I think that's probably something that needs to be done or looked into.
Sure. How has that historically gone in the past? Because, sorry if you can hear the rain in the background, it's raining quite heavily.
I don't think the docs for the blocks have been updated pretty much since they were originally written about 12 years ago or so, or 8, I guess was when they last, something like that. I could be wrong, and I'm happy to be corrected. But I
feel like that's correct. It's probably in line with my experience, because every now and then I'll go and try and read the documentation on the blocks, and it's just not at all what the block currently is. So I'm willing to agree with that. So should we just hassle the people who have written and updated blocks to write a brief description?
I mean, I can't think of much of a better way to do it, though that's been tried for many years now, relatively unsuccessfully, by the state of the documentation.
Okay.
Yeah. So we need something better, but I don't know what it is.
Yeah, this is also the problem that I'm encountering, is that it just needs to be better, but I don't actually have any great ideas on how to make it better. So yeah, well, we can discuss that later on, I guess. And then, Jonathan, I know you said something about how you are documenting how migrating to 2019 MATLAB is going. Have you got any documentation on that yet?
No, I was essentially going to update to 2019 MATLAB. I was hoping we wouldn't need significant documentation, in that the tool flow would simply update to 2019 and it would operate as it currently does. So I will document if there are any special things people need to run it, but I'm actually hopeful we won't need anything additional than what we're currently using.
Okay, cool. And then in terms of running on Ubuntu 18.04, I know we need to install KDE full. I can't actually hear myself over this rain.
Installing KDE full was the only thing I was aware of and have encountered in terms of the Snap or any of the other Xilinx dev boards I've used, the 128, the 118, etc. But I haven't tested Scarab, and as we heard yesterday, there may be some issues specifically with that.
Yeah. I had issues simulating in 18.04 with 18.04. I think in MATLAB 2019, but that was fixed by this link, so that needs to be added in somewhere as well. Any other documentation updates that need to be done off the top of anyone's head?
Issues people have had with installing, I guess, or blocks they've tried to use and found to be completely incorrect.
Sorry, can you please repeat that? I can't hear anything.
Oh, I just was wondering if anybody on the call had had issues with installing something new or similar, and if they wanted to talk about it so we could try and address it.
Yeah. Anybody? I think the most common latest issue was the virtual environment not working, but I've changed that to reflect the version that actually works. So hopefully nobody else is encountering that issue. Yeah. Okay, well, unless anybody speaks up, I'm just going to move on to the next thing. I feel like we need to have a better way of updating the documentation, because currently, as Jonathan said on Monday, it's pretty much just every now and then I'll get a random email asking for something to be added to the documentation, which can be a bit frustrating because then it's also always very vague and I'm never entirely sure what I should be adding. So I was wondering if maybe we could have a dedicated email group or something, and then list that email on the documentations, read the docs, saying like, if there's anything missing on this page, send an email to this place, and then that's monitored by a group of people. So that
I'd be fine with something like that. I'd also be fine with people raising it as an issue on GitHub, or even, editing it on GitHub and submitting the merge would also be fine. I think that should be encouraged. Like, I think, if people find something wrong, and that, ideally we want people to edit it themselves and then submit a pull request. But otherwise, perhaps raising it as an issue.
Okay, so raise as issue. Oops. GitHub. No, let's spell that. And then editing. How do you spell things? Editing from. And I think maybe we should make that more explicit, like actually have a thing that says if you find any issues, you can edit it here and then just submit a pull request and we will review it. Because maybe that's part of the problem, but I don't know. Yeah, I'm not really sure how best to go about doing this other than these methods. If anyone else has any ideas, please speak up.
I think the problem has always been related to lack of a gatekeeper for this kind of thing. It's never anyone's job to corral people to submit these fixes. And I feel like we probably say this every year. I think if it was someone's job to every 2 weeks or whatever, hit up the main code contributors and, shake them until the documentation updates fall out, and then merge them in a sort of timely manner, I think maybe everything would go a lot more smoothly. But obviously, as you well know, saying that and doing it are very different prospects.
Yeah. So I don't actually mind doing that. I think they've kind of become the unofficial keeper of documentation, at least on the Soreo side, somewhat unwillingly, but it's fine. This is just my lot in life, I guess. So I don't actually mind chasing after people. I just also am not thrilled at the idea of being the only person doing it. So yeah, I think if it was just like a small group of people who are actually keeping track of the documentation, and I don't mind spearheading that effort, but yeah.
You want a task force is what you're saying?
Yes, I want a documentation task force. That is 100% what we need.
Is it bad that I want you to have a documentation task force, but I also don't want to be on the documentation task force, which is maybe like the problem in a nutshell?
I think that is just the problem in general. Everybody wants documentation, but nobody wants to do it. But also it's absolutely fair enough. So I can't hold it against you too much. Maybe I'll just start roping people into it, and then you won't have any choice in the matter. You just end up having to do the documentation.
I mean, it's just a very social problem, isn't it? And I sort of feel like if the ball began rolling, I think, the momentum would build up. I think it's getting over this, like, no one really doing anything to help. I think, you wouldn't need to rope in many people, I think, before it started to become like a sort of core bit of the kind of Casper society.
Yeah.
Values to be a person that commits documentation.
Yeah, I think that's a good point. Just like a rapid assimilation into things. So okay, I'm good with doing that. I'm good with getting the ball rolling initially. So that's good. Thanks, Jack. I will try not to make you write any documentation.
I have this post-it note on my monitor that says just say no, but you know, if you drove the thing, I would be happy to offer some small amount of regular time to assist in whatever way is best.
Okay, cool. That's really good to know.
Because
Thank
I'm
you.
sure I'm like right at the worst end of the spectrum of people that change lots of stuff very quickly and do very little to
document it,
update the docs.
Yeah. Yeah, so I mean, that's the biggest thing, is that the problem I have mostly is that people want me like to update documentation, but don't actually tell me what to put in the documentation. So if you can just send me a thing written out to put in documentation, then I'll take care of that, because that's just a matter of copying it, pasting it into various things and making sure it's filled properly. But don't make me go and then have to sift through everything you've done to figure out the paragraph that needs documentation.
I mean, but you know, there's a huge sort of legacy problem here, particularly with Casper FPGA, where like no one knows how it works. So yeah, it's often not contributing sort of documentation for stuff you've written. It's often contributing documentation for stuff which maybe you've worked out what it does correctly.
Yeah,
I often don't feel confident enough to write down how I think things work because I'm only like 20% certain.
Well, that's at least about 15% more than I am, so you're ahead of me there. But yeah, I do see the point, and especially with Casper FPGA, Adam wanted documentation on how Casper FPGA works, and I was just like, I don't actually know if anybody knows how. So, sorry. Anyway, yeah. Okay, so I think the takeaway here is that I'm happy to spearhead. I'm going to just rope random people in. If I know that you have written a block, I'm coming for you. Sorry. That's just going to be your life from now on. I'm taking a autocratic stance on this then, since nobody else wants to do it. So yeah, is there anything else related to documentation that needs to be discussed that anybody can think of? Because
I guess maybe one thing that could be good would be to sort of have a little triage of what exists now and how, like, what areas need the most attention, because I'm sure there are some that are more egregiously out of date than others.
yeah, that's a very good point. I think the block documentation is probably the well, I mean, documentation for using Casper FPGA just doesn't exist, but the block documentation is very out of date. So that probably needs to be fairly important. And then as far as I know, everything on the current tool flow as it stands in the configuration that we know works is up to date. And then just the 2019 branch stuff and Ubuntu 18.04. Someone probably, well, I probably need to get on creating something for that. Yeah.
Like even on block documentation, there's probably some blocks that are more critical or more like interesting to users, like high-level FFT blocks, for example, would be better to document than maybe like some sort of obscure rarely used block. So
very hardware specific that nobody's used in 10 years. Yeah.
Prioritization.
Yeah.
Yeah, I mean, I think the docs for the FFT still reference the FFT for a long time ago, and it has a lot more functionality now, and all sorts of things have changed.
Yeah, but then another thing is, how do I even like figure out who to contact? Because I think the original author of that block was Aaron Parsons. Is that still?
Well, I think Andrew
probably
Martin
zero code of
work, so I'm going to throw him under the bus here. I was going to say Andrew Martins did a lot of the work, so I'm going to throw him under the bus here. But you could also check the Git logs. In theory, everything should be checked in Git, right? So we should be able to see who we can blame.
Fair enough. Okay. So that's probably the first order of business, is to just find out who is to blame for this correctness. Sure. Okay. Is there anything else? This has been a 20-minute long discussion, which is short and sweet otherwise. So I guess that's probably... Yeah.
Sorry, as Andrew Martins, can I just chip in?
Yes. Please do.
Seeing as I've been thrown under the bus. So the one I think which really helps is actual tutorials where it's not explicit documentation, but it basically shows you how to use this thing. And I'm not sure. I mean, I think we do quite a good job of keeping them up to date, and the documentation that goes with helps a lot. But there's a lot of stuff that in Casper that doesn't have tutorials and isn't in the tutorial domain, and I'm not sure if that's worth pursuing. We've had like a GPU tutorial once or twice that's fallen by the wayside. I don't know if that's worth looking at.
So have more tutorials, or see what tutorials would be necessary.
Well, yeah, I think tutorials are a good way of bringing people in.
Yeah, I really agree with that. I was also thinking that there probably also needs to be just more general tutorials and explanations of things that we do, like more low-level introductions into, DSP itself and how it relates to radio astronomy. Because I know that the spectrometer tutorials go into a bit of detail on that, but it's still assumes a fairly high understanding of very specific knowledge areas. But also, that's kind of outside the realm of what I'm able to do. So I would need to really rope people in there. So if people are happy to assist there, then that's also great.
I think the problem with tutorials has always been the infrastructure around tutorials, right? Like you need boards and you need a lab with networking, and it's like a lot of setup.
Yeah.
But maybe the specific research group or whatever stuff.
Yeah.
I don't know if that'll help with this. We can set up, GPU tutorials, say, or something. I don't know if that's workable. Maybe even FPGA stuff.
Yeah, I was thinking about that yesterday. Jonathan, you are involved in that, are you not? Can you speak to this?
As well, I can say yes, it should be doable. And Amish has just commented in the chat as well that yes, it is doable. But yeah, both for GPUs, we can request boxes with GPU that we could run, and if FPGA hardware is connected to the machines, we can also access the FPGA hardware. So we're planning on trying to have that set up as well. So one should be able to run tutorials.
Like red Patayas or something?
Yeah, red Patayas, snapboards. I was hoping we could do that at Berkeley, use the servers that we got, get them on the PRP network and hook up a snap to them. I mean, John can talk about this better, but they have several nodes with Alveos in there and other, FPGA boards. So one could run things on them as well. So that is definitely doable.
Okay, great. How far out is that from being doable, or is it currently doable now? It's just a matter of setting up tutorial.
The Alveos, I believe, are currently doable, the ones that are installed. I don't have the complete list of hardware, but John would have it and would be happy to share it, I'm sure.
Okay.
So yeah, the Alveos could be done almost immediately. Some of the other boards, we would have to find machines to hook them up to and make sure those machines were hooked into the PRP network. So that may take a little bit more admin, but I think the hardware is there. It's just a matter of sorting out how to connect it all.
Okay, cool. Maybe we can do a sort of triage there as well and figure out what tutorials would be best to get up and running first, and then get that sorted ASAP. Yeah. Okay, cool. That's very great. Thank you. Okay. Anything else? I can't find my chat, so if there is anything going on there, please let me know, because I don't know how to see that. I feel like I am an old person who can't use technology currently. So
I think the main thing, and I say this having been to 10 years of these working groups and having seen them largely be the same every year, is like some sort of action, however small, that happens on a very fast time scale. I think after this meeting ends is quite important. I think like just keeping some amount of momentum, even if it's not very much. Otherwise, we will end up having exactly the same conversation in a year's time. Although I guess we've recorded this one, so we can like play them side by side.
Yeah, I guess I've kind of created a paper trail here for myself. So, damn it. Okay, I mean, this has been bugging me for a while, this whole documentation thing, since I was first asked to start updating documentation. So I'm fully intend to get things going. Probably next week sometime, I'll have a look through everything and figure out the best course of action and reach out to some of you for some help, and build up momentum and get the ball rolling. And hopefully a year from now, things will be better. We don't have to have this exact same conversation again with the newest person taking things over. Okay, yes.
Sorry, can I just ask, with the block documentation, are we talking about on the read the docs, documenting the block, or the sort of, you know, if you double click on a block or something, there's some sort of documentation, or at some point there was documentation there kind of thing?
Oh, well, now that you mention it, probably both, because they're both quite out of date, or not out of date. So like the block descriptions are fairly vague, if there are any descriptions at all. And then the block documentation on read the docs is also quite, okay, Amish is saying he thinks that we pull documentation into a block from a web page. So update in one place, replicate and simulink. Yeah, that's a very good idea. If that's how it's done, that's fantastic. In which case, then it would just be a matter of updating the documentation on read the docs. So, yeah, I guess both, but hopefully we can kill two birds with one stone in that sense.
I think documenting in the Simulink MATLAB code is good, because you want to have the documentation for the version that you're using, not the latest version.
Yes.
And I don't know how the version matchup goes, you know, that's a little bit of a challenge, I think.
Yeah, I don't want to have the latest description on read the docs and then it's not actually what's in the block version that you're using, because you're still building for like Roach or something.
I guess right now none of them match, so maybe that's not a problem.
Yeah, everything's broken, so it doesn't actually matter currently. Okay, so block documentation in docs and
It's like we're pretty good now with like the git commit version of mlib_devel. This is what I used, but it almost is like each block needs its own versioning or something.
Yeah. I mean, kind of needs to rethink how everything is done, maybe.
Traditionally, that's how this working group ends, with this sort of existential crisis of, okay, what we really need to do is decide how we're going to do the documentation before we can worry about what it actually contains.
Yeah, I'm noticing this. I'm having slight regrets, but it's okay. My entire life is just an existential crisis at this point, so I guess one more thing isn't too much of a problem. Okay, so I'm just going to go off and figure out how to do the documentation and then tell everybody what to do. That's the stance I'm taking. And hopefully nobody leaves this hating me too much, but if so, tough. It's tough love that I'm laying down here. So, okay.
I think if you blaze the path, people will follow.
Yeah.
Yeah.
Bit like herding cats at this point, but it's fine. Okay, cool. Is there anything else anybody would like to discuss RE documentation? Any ideas that have cropped up in the last few minutes? Any glaring issues? No. Okay. I'm going to stop sharing then. If you do have any ideas or issues or whatever, please let me know. And yeah, otherwise, I think I'm happy to call this discussion finished for now, tentatively.
I guess I have one last comment, and that is that it seems like documentation is like a big, expansive kind of issue or problem or something, and maybe if it can somehow be broken down to smaller pieces, that makes it a little bit easier to take off bite-sized parts.
Yeah. So my current plan is to just go and maybe flesh out a very broad idea and then break that down into what really needs to be done and triage it a bit. And then we can build from there. Maybe it requires an entire rethink of how we do documentation. Although I think the current system works pretty well at its most basic form. The updating of documentation, not so much, that is severely broken. So yeah, we'll figure it out.
One of the benefits of having documentation and code live together is that it's less tricky to keep them in sync.
Yeah.
Still
Case in point.
necessarily, but
yeah.
I think as well there is a part of this conversation that is about resources, both in terms of people and money to pay them. That, you know, someone at some level needs to have. I mean, I know that Soreo seems to be very good at sort of formally making Casper work, you know, part of people's job descriptions and being happy to pay them for that. You know, I feel like Berkeley should maybe get a bit more involved in supporting those endeavors. Maybe there are other people around the collaboration who would be willing to sort of formalize an arrangement where some amount of somebody's time is spent on this kind of stuff. But who knows?
We keep offering to pay you, Jack, but you keep refusing.
I've got to sort out a few conflicts of interest first.
I think also if it's easy to if you make it easy for users to make changes and submit them, then if they're like working with a block and they find documentation doesn't match or something and they can change one little bit to help them out and they can get that contributed, you know, reduce that sort of barrier to contribution, that would be very helpful as well.
Yeah, that's a good point. And also, I think it just also needs to be more explicit that edits are actually welcome from the collaboration at large, because it doesn't actually say that anywhere. I think it just, actually, I don't think there's anything other than a Sphinx README page somewhere in the documentation on how to update the documentation, but you only get there if you have the intent of updating things already, and you just find yourself on that page naturally. So maybe that should be the first thing, is just explicitly making it clear that please update the documentation as you see fit. Okay, cool. What happens now, considering this ended half an hour, is winding down half an hour early? Anybody on the organizing committee can speak to that?
I think traditionally you get in a beer before the closing talk.
Yeah. Unfortunately, well, I mean, I've got some here, but I don't know how I'll get it to anyone else.
You're a bit far away.
Yeah,
I'm sure the RFI discussion is still ongoing, so maybe we just break and come back at 11 for well, I suppose there was a break, then there was more discussion, and then there was the conference wrap up, but maybe break and come back at 11 California time, I guess, so 8 o'clock South Africa or 1800 GMT, and see if there's anything else has come up, and then we can wrap up then.
Awesome.
Cool.
Or crash the RFI meeting as well.
Yeah.
That's you. Okay, awesome. Thanks, everyone.
Thanks, Mark.
Yeah, thanks.
Melissa or Ryan, can I just check my screen sharing quickly?
Yes, go ahead.
Mm-hmm. Let's see.
All right, it seems like the RFI discussion is coming to a close, so we might start to have an influx of people soon.
Mm-hmm. Mm-hmm. Should I just keep this on? Is that cool?
Yeah, you can just keep that on, I think.
Then also worth checking, because I'm just moving it from screen to screen. Can you still see it?
Yes, I can still see it. I don't see you moving from screen to screen.
Excellent. Excellent.
All right, let's maybe give another minute for people who are rejoining from the RFI room. We ended up using the whole time.
Nice. Did you want to give the RFI room a short break, or do you want to get straight into it?
I think we could get straight into it, but maybe just give another minute
yeah.
because people are
Sure.
finding the Zoom link.
Of course.
Well, why don't we get started? So for our last talk of the conference, Amish is going to give a summary looking back on the week and looking forward to next things. And I just want to say thank you all for attending. And it's the first online Casper conference, first time I've ever organized a conference. And thank you all for making it a nice week. Go ahead, Amish.
Cool. Well, I got to reciprocate and return a thanks straight back to you. Thanks to Catherine and the LOC for just keeping tabs on things and ultimately making this happen. But of course, thank you to attendees and speakers and anyone on YouTube passing by, or indeed sticking with us throughout the day, thank you for coming, because it's one thing to organize a conference, which is interesting in its own way. Without attendees, does the conference actually ever happen? We know it's not the usual in-person conference, obviously, but we're playing the hand we're dealt, and I think it went pretty well. I gotta admit. And I guess you could all give yourself pats on the back for making it through, all time zones and everything. A further reminder, just don't let this be the end of any conversations you've had or been having during the week. That kind of is the whole point of Casper, is that you continue collaborating for as long as you deem necessary or want or can. The Casper Astro Slack, of course, has been open long before this conference and will continue to be open to anyone wanting to get involved with Casper. I'm also using a new slide deck, and I'm not even sure what animations are built in. So let's all find out together. But as the new tech out of NVIDIA networking is called What Just Happened, we can apply that to this week. There were discussions about the more traditional avenue of Casper development, things we've been discussing in telecoms for the past while, things we all know and love. Further on to new things like GPUs, pipelines, engines, images, everything in between. After that, promising work being done with heterogeneous backend systems. I think there's some suspiciously cool stuff happening right underneath our noses at times. Vinand, Nitish, Gerrit, Hari, thank you for sharing, and I'm sure there's countless others out there fighting this fight. To our open source neighbors at GNU Radio, thank you very much for visiting. Always a pleasure. And like Catherine said, where do we go from here? To start off with, in a bit more detail, FPGAs. Well, Mitch Burnett from BYU, he has been leading the charge against unsupported RSOC platforms in the Casper tool for some time now. And this has already been snapped up and implemented by Jenny Smith and Arash. That's been very, very cool to see happening in very different ways. There was also quite a cool demo from Robert Anderson at MathWorks, which is quite interesting. I think there'll be a keen eye on that. On the other side of things, well, Alveos and Vitis, I think this has also been something that we've been discussing for some time, but with mixed results, let's say. I call it vicarious Vitis development in every sense of the word. There's some, maybe things might be made a bit easier with Robert's presentation, but looking at the notes from the tool flow discussion the other day, there's a lot of to be elaborated bits, and hopefully there'll be good progress soon. I linked the blog post here for anyone watching this back or wanting to get involved in this kind of space. This seems to outline the differences quite well, I think, and quite succinctly. Certainly some hits and misses in the early stages of development here, but as far as I know, all boards are alive and well and live to fight another day. ADCs, the thing is, I personally don't have a lot of involvement in ADCs, but I know this is a very interesting topic, least of which coming from Bill Jenkins in the last invited talk. Not even just in a Casper sense, in a world sense. Homan, if you're watching this, thank you very much for still presenting, even though you're quite far east, as I said. Jonathan Weintraub's master list of ADCs always comes in handy, and he also shared a newer resource on a report on high-speed ADCs and any problems using those. From there, like I said, GPUs, lots of new developments in this space, and it even had its own day of presentations. Good talks from people who have been working in the space for some time now, and also newcomers. I gotta say, including myself and us at Cereo. John Romain, thank you once again for presenting and sharing your work with us. It's come in very handy, and already sparked conversations outside of the Casper week for myself. And everything ranging from overviews, considering the time for presentations, detailed explanations outside of the presentation time, and great discussions during the discussion working group. That was fantastic. I have to mention talks by NVIDIA as well. This really was the first Casper, and in smaller font for something that will keep me warm at night, knowing that there was a talk by a GPU vendor at a Casper conference and chaired by Jack. Always good fun. Another word on our open source neighbors at GNU Radio. Also very cool stuff they're aiming to do. Just, I think, seems like we're all recognizing various gaps in our tool flows, and more importantly, trying to rectify that. So Derek, Bastian, Josh, Mike, thank you for sharing your work and ideas. I think I'll definitely be attending GRCon this year for any updates. On from there, well, like I said, heterogeneous backend systems, it's inexpensive configurations can lead to pretty extraordinary results. And of course, we can't mention the Pacific Research Platform. Thank you, John Graham, for a pretty cool rundown and run through of how we can get involved there. I know a lot of people are going to be taking you up on that offer. Thanks to Dave McMahon for the slide. It seems like not even one, but 2 lifetimes ago, 2013, but this is where we are now. If I could share some, not so much confidential information, but something that Gerrit certainly undersold in his presentation. He mentioned to me that he ran into some problems with his board development with the Xilinx DMA IP. So he ended up writing his own basic DMA engine specifically to target his application. And if that doesn't sum up Casper, then I'm not sure what does. So there you go. HDL development, well, there's still some of that. There always has to be. The battle still continues between kind of OpenCL and or HLS side of life and then sort of artisanal crafted HDL and DSP. But ultimately, both need continued buy-in from developers to survive. And the longer we see more people involved in both sectors, ultimately I think it's good for everyone because it keeps the competition going. We even had presentations on automated workflows. I don't think anyone would ever think there would be discussions around microservices at the Casper table, Jenkins and continuous integration and so on. RFI and documentation. Well, I put the placeholders in here because I was in the documentation discussion group, and the note I made is it was much of the same really, which is both good and bad. I think anyone watching the recording back will see. It seems like the same discussion kind of happens every year, which in one way is good because people are still on it, but on the other angle, it is bad because how much is being taken forward. RFI, I mean, I know the RFI group went on through their break time, and I'm not sure if anyone wants to chime in now or afterwards, but I know we're going to chat for a bit after this, but please do add where you see fit. And of course, the speakers. I was going to say Casper, it's young and old, but that might be taken the wrong way. It's more new and familiar faces or usernames even. So thank you for contributing. I mentioned these speakers by name to give people an idea of the range of topics covered and discussed this week. And I have to be honest, as great as everyone has been, a late entry for best talk for me personally was Bill Jenkins from Intel. The stats and info on the ADC tile module specifically really did have me on the proverbial and sometimes literal edge of my seat. I know I was messaging Jonathan Koch for a bit there as well. I guess ultimately that's a good thing as well. Xilinx have had a strong foothold in Casper's development for some time, and it's about time someone else, quote unquote, disrupts that. Overall, you can gauge from here, it's GPUs and DPUs and heterogeneous platforms, it's even smarter NICs than before. They're all coming to the fore and in some ways becoming more easy to interact with. And an honorary mention to the networking components and infrastructure that in my mind, never seems to get a dedicated talk. Hopefully that'll change, but there's really interesting work overlapping in that space as well. And to end, I mean, the closeout talk isn't necessarily the closing out of the collaboration. It's a reminder that this still continues outside of whenever any of us meet in small or large numbers. Please do continue to spread the word of Casper and Casper involvement. I mean, continue to work with the tools, continue to interrogate and complain about why things don't work a certain way, because that means someone needs to continue working on it. The reach of Casper involvement and usage only grows with you sharing it onto the next person. And a certain Brian Bradford knows this all too well. So one of the yesterday's speakers as well, Brent Craner, mentioned that most of the time this week, terms were thrown around that just went over his head. And Jenny Smith was quick to point out that it does get better. So please do continue to speak to us, to join the main mailing list, join the dev list, come and visit at one of our telecons, and just let us know how it goes. I think that's me for now.
Thank you, Amish. If I think you said you wanted there to be some discussion afterwards.
I mean, I saw Kaushal send me the notes from the RFI discussion as I was presenting. So it may not have been the most seamless transition to opening that up, but if Kaushal or even Catherine, I think you were in that discussion group, if there's any particular points you wanted to share.
Well, there was quite a bit of discussion about flagging impulsive events in time domain versus frequency domain. That was something that stood out to me as especially interesting.
That's cool. Is anyone particularly working in that space? Can I call it?
So I think maybe Kaushal has more to say about this.
Yeah, so the discussion was mostly about how to try weighing the visibilities based on flagging the time domain impulsive RFI. So I think as of now, there is no end-to-end solution to this problem, because this kind of flagging is done much in the beginning of the receiver, the signal processing chain. So it's difficult to first convert those time domain flags to frequency domain and then propagate it through the entire system. So we were just pondering on it, and we just so no, as of now, I think there is no solution.
No, I think that's kind of why these discussion groups happen. It's not necessarily to come up with a solution. Sometimes it's just about identifying where the problem is. And that's as good as it can get some days.
Yeah. And I think one more point which there are various points on different estimation techniques and then what would be better and what not. And but one thing which we discussed today was can we have a RFI database across Casper, and particularly Francois was saying that SARAO RFI working group might have a certain kind of
oh, that's very true.
And because we are now going towards learning based techniques, so if there is already classified data, labeled data, then it will help everyone test their techniques, algorithms. So that was something I think going further. So
that would be very cool.
Yeah, we need to see if such a thing can be developed.
I'm sure a lot of us will be keeping an eye out for that.
Yeah, so I think that in a nutshell was about it.
Sounds awesome. Catherine, did you want to add? Not necessarily about that, just in general.
About other discussion topics, or just ending the conference, or?
And anything. Francois, I see you unmuted.
Catherine, sorry, maybe we should just mention the advisory board meeting.
Yes, it will be tomorrow at 7:30 7:30 Pacific time. Francois, were you thinking just asking for feedback for then? I was planning to send a workshop survey a little bit after to get a general sense of how our first online workshop went.
That would be great, yeah. But if anyone had feedback, they could send it to any of us.
Yes.
Yeah, I think beyond the workshop, if people have particular suggestions for future directions for Casper, or ways that we could collaborate, improve our collaboration, or criticisms, constructive criticisms, things that we could do better, not just about the workshop. It'd be great if you can contact, perhaps by email, one of the Casper advisory board members before our meeting, which is, I'm sorry to give it in Pacific time, but it's 7:30 in the morning Pacific time, which tomorrow morning, Friday morning. So we'd appreciate any advice or suggestions. Thanks.
Can I post the advisory board email in the chat? Will it work? Can anyone send to that?
Yes, it should work.
Okay, well, there it is, in case you don't have an email address for one of us. So if you have anything to suggest, feel free. And look out, please, for Catherine's survey. It'd be great to hear what you think of the workshop.
All right. Well, thank you all for a really great workshop, and see you hopefully in person next time.
Thanks, Catherine, for all your hard work. It was fantastic.
I think we should unmute and applaud.
Catherine, when you said our first online, our first virtual workshop, I was saying, I hope the next one's not. But this was wonderful. Thank you.
Thank you.
And thanks also to Melissa and Ryan in the background who kept it all running smoothly. Thank you.